Let's do one example of changing coordinates and changing bases. So imagine you have a vector field, and for the moment let's forget about mathematics. Let's only look at how this field looks like. Okay, this is a field defined in 2 dimensions, so that for each position, for example at this point, for each point we have an associated vector. Okay, this could be the electric field, or it could be the speed of air, so this is indicating wind, or whatever it is, it's a vector field. Now for a different position, if you go here, now the vector has a different value. It's a different vector with a different direction and a different length of the vector. Yeah. So this is our vector field, and this is a physical reality. This physical reality doesn't care if we use rectangular, if we use polar coordinates or bases. It doesn't care. It's the same field. But we need to find mathematical ways of describing it. And as I said, we have 4 combinations. So we can either have rectangular coordinates and rectangular bases, or rectangular coordinates and polar bases, or polar coordinates and rectangular bases, or polar coordinates and polar bases, right? We have in total 4 combinations, which are our 4 slots here. Okay. Now for this particular field that I plotted here, it corresponds to this expression, mathematical expression here. Okay. And this mathematical expression is written in which coordinates? Well, do you see xy or do you see rho phi? Do you see xy? So then the scalar things, you are not looking for vectors when you are trying to decide what coordinates is this written in. We are looking at the scalars, yeah, not the vectors. So these are clearly rectangular coordinates. What is the basis of this field? In which basis it is expressed? Then we have to look at the vectors. So where are the vectors here? We have x hat and y hat. So this is clearly rectangular basis. Okay. Therefore, this mathematical expression represents this field in the first quadrant, rectangular coordinates and rectangular bases. So what we are going to do is we are going to fill up the other 3 quadrants. So you are going to practice changing coordinates and changing bases. Okay. So let's do it this way. We are going to jump first from here to here. Then we are first going to change the coordinates. Then we are going to actually change the bases. So we are going to jump from here to here. That will be our second step. And then when you are here, you are going to change the bases, change the coordinates back to rectangular, but keeping the polar bases. Okay? So we are going to do this third. And now you might ask, why did you do it this way and not the other way around? Well, it doesn't matter. Okay? Actually, it might be easier or more difficult doing it one way or the other. The calculations will be different, but the final result is going to always be the same. So the final table is always going to be the same. Okay? Okay, so step 1. We want to change from rectangular coordinates to polar coordinates. So we start with our function, which is a vector function of xy, and we are going to substitute x. Wherever we see an x, we're going to write rho cosine phi. And whenever we see a y, we're going to write rho sine phi. How do I know this? Well, as usual, this is just given in the equation list. So this is the polar coordinates, x and y as a function of rho and phi. Okay? So if we do this, so our initial function was x minus y x hat, so that will change into rho cosine phi minus rho sine phi x hat plus x plus y y hat. So this is rho cosine phi plus rho sine phi y hat. Okay, and this can actually be, we can take rho as a common term, so we could actually write this as rho times cosine phi minus sine phi x hat plus cosine phi plus sine phi y hat. Okay, so this is it. This is the function written in polar coordinates, but still in rectangular basis. So we can write that in this quadrant. Okay, so you see that this is really the very easy step. Now comes the slightly trickier step, which is this step number 2, changing the basis. So let's do step number 2, change the basis. To polar basis. So we want to change from x hat, y hat, we want to change to e rho hat, e phi hat. Okay? And we know the expressions for e rho hat and e phi hat because we have them in the equations. So I have them in my second monitor here. Let me copy them. And this, in my experience, is the least favorite step of students. I think for the reason that there are many ways of doing it. And you seem to not like when there are many ways of doing it. Why don't you teach me one way? And that's it. I understand it's easier to only have one way, but reality is reality. This is maths. Often there are many ways of doing the same thing. So what were the different ways? So let's walk through them. So one way was to project using the inner product. So first let's define what we want to do. We have f, so we have the x component times x hat plus the y component times y hat. And we want to arrive at the same f, but written as the rho component times e rho hat plus the phi component times e phi hat. So the first way of doing it was to use inner product, projection using inner product. Which was to say that f is equal to the projection of f into e rho hat in the direction of e rho hat. Yeah, that's the projection into e rho hat, plus the projection into the direction of phi, which is inner product of f with e phi hat times e phi hat. So let's do that. So this is equal to the inner product between vector f, and we write this vector in x hat, y hat basis. So we have cosine phi minus sine phi, that's the first component. And the second component is cosine plus sine. So this is vector f written in x hat, y hat. Actually, it has a rho always in both components. So let's keep that. Let's keep that. Okay, so that is the vector f. Now this is inner product with e rho hat, and e rho hat we have it here. So the first component is cosine phi, and the second component is sine of phi. And this inner product is then multiplied by e rho hat, and then plus. I'm going to do the same. I'm going to copy this. I'm going to duplicate this and just change it slightly. Plus this times e phi hat. So what do I need to change? So f is the same. So f, I can leave it. So this I can leave the same as this. I only need to change e phi hat. So e phi hat is minus sine cosine. Minus sine and cosine. Okay? So now I can do this. And how do you do the inner product between these two vectors? You do this times complex conjugate of this. Actually, every vector here is real, so let's forget about the complex conjugate. The inner product is just the dot product in this case. So it's this times this plus this times this, and that will give us f of rho. So the rho component of the vector. And then we do this times this plus this times this, and that will give us f of phi. Okay? So probably this will involve having cosine squares and sine squares and some simplifications for sure. Yeah? But you know how to do this inner product. So I'm not going to continue on this path. Instead, I'm going to tell you that there is another path, which is use a change of basis matrix. So remember how this worked. We define our matrix A, which has E rho hat as the first column and E phi hat as the second column. So this is equal to E rho hat is cosine phi sine phi. That's E rho hat. And E phi hat is minus sine phi cosine phi. Now we need to find its inverse. And now let me be a bit sneaky here. So we know that these unit vectors are an orthonormal basis. And you remember from the matrices chapter that when a matrix has the columns as orthonormal bases, this matrix is a unitary matrix. And therefore, its inverse is equal to its Hermitian conjugate. So you don't even have to calculate the inverse. You can just do the Hermitian conjugate. In this case, since all the elements are real, the Hermitian conjugate becomes equal to the transpose. And therefore, the inverse of A is simply the transpose of A. So the first column becomes the first row, and the second column becomes the second row. So now this is the inverse. And what does this mean? Well, now this means that the function, the vector written in row phi basis, so our vector f, is equal to the inverse of A times fx fy. So this is equal to, I'm going to copy the matrix for the inverse, and now I'm going to copy the vector for f, which we have written right here. That's the vector for f. So let me duplicate that and place it here. Okay, so now we can multiply this matrix times this vector, which has two elements, and we will find a vector with two elements, and those two elements will be f rho and f phi, the two components. Okay, but now finally, what is even easier? So even easier is to, by inspection, we identify. So if you look at the shape of f, which is here, you actually see that this is equal to, let me copy it. So you actually notice that this is equal to rho times cosine phi x hat plus sine phi y hat plus minus sine phi x hat plus cosine phi y hat. Right? I just reordered the terms. And now you notice that this is actually equal to E rho hat, and this is actually equal to E phi hat. So you don't have to do all of the above calculations. You just know that this is equal to, I'm running out of space here, let me continue back down here. This is equal to rho times E phi hat plus E rho hat plus E phi hat. Okay, so now you know that this is how you write it in polar basis. So in my opinion, this third option was obviously the easiest option. You didn't have to do inner products, and you didn't have to do inverses and matrix multiplication. Okay, but what does this mean? What is the value of f? So what is now that you have seen the answer, which we can copy into our table? So what is the value of f rho and of f phi? So f rho is whatever multiplies E rho hat, so it's equal to rho, and f phi is also equal to rho. Okay, which means that this inner product, once you do it, you should get rho as the answer, and this inner product, once you do it, you should get rho as the answer. Okay, and that's because the cosines and sines will cancel out. They will, cosine squared plus sine squared will be equal to 1, and so on. The same here. When you multiply this matrix times this vector, you should have arrived at a vector equal to rho. Let me write it. Equals rho, rho. Okay, so it's a vector that is rho in both elements, both coordinates. Okay, so when you write it in this way, it's rho times E rho hat plus rho times E phi hat. Okay, excellent. So now we have these two filled in. Now we are missing one of them. So clearly the easiest way here would be to change the coordinates back to rectangular. So how do we change the coordinates? So remember, every single coordinate that you see here, in this case rho is the only coordinate that you see. These are not coordinates, these are unit vectors, so we are not changing those. We are changing the coordinate rho. We need to change it into x and y. So how do you do this? Well, if x equals rho cosine phi and y equals rho sine phi, then rho is equal to square root of x squared plus y squared, right? You can either figure this out mathematically, or you can actually do it by reasoning, that if you have a certain value of x and a certain value of y, and you're looking at this point, then of course rho is simply, using Pythagoras' theorem, is the square root of x squared plus y squared. Okay, so we can just substitute this value for rho, square root of x squared plus y squared. Okay, so we substitute this into rho, and we arrive at this. And now we have filled in the last quadrant of this table. So notice that this expression, what are the coordinates? What are the things that are not a vector? We have x and y, so it's rectangular coordinates. That's why we are on the left column. But what is the basis? What are the vectors? The vectors are E rho hat and E phi hat, because we are in polar basis. That's why we are in the second row. Okay? So now, looking at these four expressions, I can ask you, the four expressions represent the same field, but which one is simpler? This one, by far, yeah? Also, this one gives you a lot of intuition. So this expression is telling us that the length of the vectors, so where the length of the vectors will be rho. So this is actually, we can see this here. If you are very close to the origin, the length of the vectors is tiny. When you move farther away, the length of the vector increases a little bit. And if you move either more far away, then the length of the vectors is biggest. Yeah. So the further away you are from the origin, the bigger this vector is, the length of this vector. And what is the direction of this vector? The direction is both in the direction of rho and in the direction of phi. So it's a superposition of both. So remember, for example, here, remember that E rho was this direction, in the direction of the radius, and E phi was in the direction of tangent to the circle. Yeah. So now we know that the direction is E rho plus E phi. So it's a linear combination of those two vectors with the same amplitude. So therefore it's pointing up in this case. Yeah. So we know that the direction is always going to be pointing somewhere between the two vectors, E rho and E hat. So in this case they are pointing in this direction, and so on. So it's telling us about the direction of the field. So clearly, when you saw this expression, it would have been very difficult to figure out how this looks like. However, if you see this expression, it's much easier to think how this looks like. Okay, so that's the advantages of changing coordinates and of changing bases. Thank you for watching.